Okay, thank you.
Yes, we can see it.
Yeah. So at least the system works.
Yeah, it's working good, but he has to put it. Mohammed, could you put it full screen, please?
Okay. I'll put it full screen. 1 second, please.
Okay. It's 3 minutes. You have 3 minutes.
Okay, I'm ready. I think it is full screen now.
Yes.
Yeah, it looks full screen to me. Yeah. So we should be fine.
Okay, sir.
We'll wait for 1 more minute, maybe 1 or 1.5 minute before we start. So you could, Mohammed,
So when
maybe
you tell me start, I will start. Okay.
Yeah, you can stop the share for now.
Okay.
Yeah, because everything will be working.
Okay, sir.
And let's see. Great.
Gilbert Palafox 4552. Gilbert Palafox 4552.
Okay, everyone. It's 12:59 p.m. California time. Welcome to EPMM-1, Electronic Photonics and Magnetic Materials. So this symposium will have 11 speakers, and I will send several emails to emphasize we do need to stick with the schedule. So without much ado, let's start with our first speaker, Mohammed Abu Almad. I hope I pronounce your last name correctly.
Abul Magd.
Yeah, so yeah, go ahead, Mohammed.
Okay, sir.
Magneto-caloric effect, magnetothermal and the elastic properties of samarium iron 3 and the erbium iron 3 compound. We present this work in cooperation with 3 Egyptian universities, Helwan, Damietta, and Shrouk. Outline, introduction, aim of the work, basic equation, results, conclusions. Introduction. The magnetocaloric effect is defined as a heating or cooling, that is temperature change, of a magnetic material due to the application of a magnetic field. Nowadays, there is a great deal of interest in using the magnetocaloric effect as an alternative technology for refrigeration. The magnetic refrigeration offers the prospect of an energy-efficient and friendly environment. Aim of the work: calculating the elastic property of samarium iron 3 using first principle calculation as implemented in the PIN2K electronic code. Calculating the magnetothermal and magnetocaloric properties of the two systems, samarium iron 3 and the erbium iron 3, using the mean field analysis and the standard relation for the total heat capacity. Discussing the results of our calculation in the light of available experimental data to show the validity of the calculation methods we used. Basic equation of magnetization. According to mean field theory, based on the two sublattice model, the total magnetization is equal to the molecular field of the rare earth plus 3 iron sublattices, where the Brillouin function controls the temperature dependence of each sublattice moment. Basic equation of heat capacity. The total heat capacity is a contribution from 3 components: electronic, lattice, and magnetic. The electronic heat capacity calculated by simulating the electron density of state at Fermi energy by V2K software. The lattice heat capacity is obtained by performing the integration where the by temperature is a limit. The by temperature comes from the longitudinal and transverse velocities. The latest is obtained from the simulated shear and bulk moduli. The magnetic heat capacity was calculated through mean field theory. Basic equation of Magneto-Caloric effect. The basic equation for calculating the Magneto-Caloric effect is a contribution from two main processes, isothermal and adiabatic. For the isothermal case, we simulated the integration of the derivative of magnetization, and for the adiabatic case, we simulated the above integration multiplied by temperature divided by total heat capacity. This has been done through the very powerful mathematical software. Results of magnetization. Our simulation for the erbium iron 3 magnetization show a ferromagnetic coupling with a compensation point at 220 K, while the samarium iron 3 shows a ferromagnetic coupling in agreement with available experimental data. Results of heat capacity. The temperature dependence of the magnetic specific heat of erbium iron 3 in different fields shows a field dependence close to Tc is an indicative of a second order phase transition, and the total specific heat at different fields is shown. Results of entropy. Magnetic entropy for samarium iron 3, a decrease in magnetic entropy is found with increasing the magnetic field saturation takes place at T greater than Tc. Result of elastic moduli. The calculated elastic moduli, shear, bulk, Young and Poisson's coefficient for the rhombohedral samarium iron 3 compound. Result of change in entropy. The isothermal change in entropy calculated by the trapezoidal method for erbium iron 3 at different fields, both direct and inverse magnetocaloric effect is shown for this ferromagnetic compound. The isothermal change in entropy calculated by the trapezoidal method for samarium iron 3 at different fields. Only direct magnetocaloric effect is shown for this ferromagnetic compound. Result of adiabatic change in temperature. The temperature dependence, or T, divided by the total specific heat on temperature at different fields for erbium iron 3. Weak field dependence is shown. Similar behavior is found for the samarium iron 3 system. This weak field dependence justifies using the following equation to calculate the adiabatic change in temperature. Adiabatic change in temperature versus temperature in different fields for erbium iron 3. Both direct and inverse magnetocaloric effects are shown. Adiabatic change in temperature versus temperature in different fields for samarium iron 3. Only direct magnetocaloric effect is shown. Conclusion. The bulk, shear moduli, and the electronic density of state are calculated using the V2K ab initio electronic code. The by temperature for samarium iron 3 and erbium iron 3 compounds are 459 and 359 Kelvin respectively. The electronic coefficient of heat capacity is 70 and 25 millijoule per mole per Kelvin square respectively. Ferrimagnetic and ferromagnetic behavior are found in erbium iron 3 and samarium iron 3 compounds respectively. Direct magnetocaloric effect and both direct and inverse magnetocaloric effect are found in the samarium iron 3 and the erbium iron 3 respectively. Maximum cooling rate in a 7 Tesla field is about 0.85 Kelvin for each Tesla for the two compounds, samarium iron 3 and erbium iron 3. The temperature and field dependence of the magnetization, magnetic heat capacity and entropy and magnetocaloric effect quantities are all indicative of a second order phase transition in this system. Thank you very much.
Great, thanks a lot. So we have time for questions. I believe you can unmute yourself and just speak up directly, or if you prefer, you can type into the chat window. I'll wait for 1 more minute. Thank you for stick with the time, Mohammed, and thank you for the talk.
Thank you, sir.
Thank you. Let's move to our second talk by Magneto-Caloric. Again, I'm sorry if I pronounce your last name not very well. Yes, go ahead. You can.
I'm going to share. Okay. Can everyone see my screen?
Yep.
Yep. Okay.
Yeah.
Hello, my name is Gökçe, and I'm joining from Istanbul. Today, I'm going to talk about microparticle production specifically designed to use in transcatheter arterial chemoembolization applications. Chemoembolization is a protocol procedure that is used to treat cancerous tumors. Usually in clinical applications, polymeric beads and polymeric particles are used. But in this study, we used magnetic and clay mineral particles to obtain chemoembolization particles. Today, I'm going to talk about them. First, I'm going to talk about what transcatheter arterial chemoembolization is and what particles are used in this procedure and their disadvantages. Later on, I will talk about why magnetic and clay mineral particles are a good alternative for polymeric particles. Finally, I will talk about our particle production methods and our results, experimental results. Transcatheter arterial chemoembolization is a procedure that blocks tumor blood supply and delivers chemotherapy agents to the tumor sites at the same time. Via catheters, embolic particles are delivered to the tumor site, and these drug-delivering particles simultaneously block the tumor blood supply and deliver chemotherapy agents, and this results in ischemia and chemotherapy at the same time, which results in shrinkage of the tumor and or necrosis of the tumor. These particles should be greater than 20 micrometers in order to embolize the tumor. Also, imaging plays a crucial role in this procedure. These used particles should be radio-opaque in order to assist the operating radiologist during the procedure. This chemoembolization procedure is most commonly used clinically in certain types of tumors, such as liver and kidney tumors. But the particles that are used are, as I mentioned before, mostly polymer beads mixed with X-ray contrast media. There are several disadvantages to these particles. The contrast media and the beads can separate during the administration. Also, there's a rapid and burst drug release response to these particles. Also, some particles, mostly hydrogels, can be compacted during the administration. Multifunctional particles, to overcome these disadvantages, multifunctional particles could be used. And other particles that have improved drug loading and drug releasing abilities could significantly change the outcome of this chemoembolization procedure. As I mentioned before, we used magnetic particles and clay mineral particles to produce two different types of chemoembolization particles. First of all, why did we use magnetic nanoparticles? Specifically, the magnetic hyperthermia was in our interest. as we know, magnetic particles can be heated under alternating magnetic fields, and this is a known fact that chemotherapy drugs work more effectively when the temperature of the tumor is increased. Also, the temperature increase in temperature damages the tumor itself while administering the drug. Okay, why did we choose clay-based particles? Clay-based particles, mineral particles are widely used in pharmaceutical formulations. They have a non-toxic makeup and high absorption capacity, and they demonstrate a significantly extended drug release response. Okay, our production methods, I will explain them here. If you can see my mouse, we linked these nano-iron oxide particles together via bridging flocculation using a polyvinyl provolone polymer. Later on, we coated the outer surface with another polymer, hydroxyethylene cellulose. Finally, we loaded doxorubicin, which is an anti-tumor drug, onto the surface. If we move on to the clay mineral particles, we use bentonite here. We loaded bentonite with doxorubicin and X-ray contrast media via adsorption method. Later, let me talk about the results of our study. First, if we can look, I will explain the magnetic particle ones. In order to obtain this linked structure, as I mentioned before, we used bridging flocculation. We obtained the concentration range of the polyvinyl provolone where the bridging flocculation occurs. So then we linked them together. After we coated the hydroxyethyl cellulose, here we can see that as the hydroxyethyl cellulose concentration increases, the particle size increases. We chose 5 grams per liter one for hydroxyethyl cellulose because the particle size was approximately about 70 micrometer, which was suitable for chemoembolization applications. Later on, as I mentioned before, we loaded doxorubicin onto the surface. Here we can see that loading efficiency was about 35%, which is low, I know, but later when I show the in vitro results, it was sufficient enough to kill cancer cells. Oh, sorry. When we look at the drug release response at pH 6.8, which is tumor pH, the 80% of the drug was released within 12 hours, which was not rapid as polymeric beads. It was slightly extended. And when we heated our particles under alternating magnetic fields, we saw that they reached to 55 degrees Celsius within 110 seconds, which indicated that our particles could be used in magnetic hyperthermia treatments. Later on, when we tested our particles in cancer cell line, cancer cell lines, MCF7, which is a human breast cancer cell line. Here we can see that our magnetic particles were effective as pure DOX, which is represented in orange bars here, at the highest concentration. But as the concentration lowered, the gap between pure DOX and the particles were increased, which indicates that we should use the highest concentration when using it for chemoembolization applications. Here we tested in vivo, and we can see that this is before embolization. The blood flow is quite normal. After we administered our particles, we can see that blood flow here at the tumor site was cut off, which indicated that embolization was successful. If we move on to clay-based particles, this figure B is the picture of our final product. Here we have, X-ray contrast media and doxorubicin loaded onto these particles. We can see that when we loaded them onto the clay mineral particles, the particle size increased to 21 micrometers, which is also suitable for embolization. When we look at the drug loading capacity, the clay minerals were significantly higher than magnetic particles at 99.6%. When also we look at the drug release behavior, it is also different than magnetic particles. We can see that about up to 55% of the drug was released within 20 days, which is a significant difference between the magnetic particles. Here we can see this cell viability of, again, MCF7 cell lines of pure DOCs and our clay-based particles. We can see that at all concentrations, clay-based particles perform similarly to pure DOCs. Also here, finally, in vivo tests show that clay-based particles were also able to embolize the tumor. Here we can see that blood flow was stopped here. In addition to embolization, clay-based particles were imaged under computed tomography. Here we can see the particles clearly in the tumor area. Okay, finally, in conclusion, each particle performed and was effective in its own way, depending on the desired outcome or the treatment method. Each particle has a potential to be used as chemoembolization particles. Of course, further studies are required, but both seem to have quite good potentials to be chemoembolization particles. Okay, thank you very much. If you have any questions, I don't know if we have time or not, I can answer them, or you can mail me at this address. I will be very happy.
Thank you, Mehdi. You used 10 minutes, but we do have time if there's a quick question. So if not, yeah, as Mehdi said, you can always email our speakers. Yeah. Let's move on to our next speaker, Wei Guoyin. So if you can unshare your screen.
Okay.
So our next speaker is Wei Guoyin. Go ahead and share your screen and start your talk. Yeah. And you're not in the presentation mode yet. And you need to unmute yourself. Yeah.
Okay. Wani, is that okay?
Yeah. Yeah. Looks great. Go ahead.
Okay. Good afternoon, everyone. My name is Wei Guoyin. On behalf of my colleagues, Alex Svelik and Robert Collick, I would like to thank the organizers for giving us the opportunity to present our work on novel magnetism in mixed 3D and 5D transition metal compounds. 3D compounds such as cupric superconductors are known to host complex phase diagrams, which can be tuned by small perturbation. But recently, the relativistic model insulators was found in unidates due to strong spin orbital coupling. So here we try to present an approach that's combining 3D and 5D atoms in those mixed 3D 5D compounds to see some novel magnetism. Okay, multiple insulators actually put in a simple way is that when the local Coulomb interaction is larger than the bandwidth, so then we have multiple insulators. This does not in general hold in the 5D materials because of the more extended orbitals. However, because of spin order coupling, is proportional to the fourth order of the atom number. So in 5D material atoms, it is pretty large compared with the local Coulomb interaction U and the spin orbital and the crystal field splitting. So this could be split the wide band 5D band to a narrow band near the Fermi level, as shown in this iridium. This iridium 4+ has 5D electrons upon large crystal field splitting. So you have T2G orbitals are effective, and then upon this large spin orbital coupling splitting, so we have those low-lying full field total angular momentum 3/2 states, and this effective 1/2 pseudo spin states. This form a narrow band near the Fermi level. And what's special about this pseudo spin state is that you have a composition of different orbitals. You have 3 T2G orbitals right here. So this internal degree of freedom will open a pathway to novel exchange pathways. So I'm sorry, here this is automatically showing up because I recorded it here. So I have to catch up with the automatic mouse here. And then for this material, for example, this is a copper. The blue circle is copper, and then this is iridium. They form a chain structure. So for the copper, you have a real spin, and for iridium, you have a pseudo spin. So this material is exchanged in several ways. One is that it's ferromagnetic, and versus the other isostructural material, 3D and 5D materials, they are antiferromagnetic. Also, this material has a large magnetic excitation gap. In disagreement with the isotropic, the gapless spin half ferromagnetic Heisenberg model started before. And also, it's a ferromagnetic, but its saturation magnetic moment is very small. So it's 0.5, not 2. And also, it's a ferromagnetic, but it displays antiferromagnetic wise temperature. So what's the mechanism? And first is that the relative orbitals is that the couple 2+ has x squared minus y squared orbitals as the active orbital. And for the iridium, you have x, y, and y, z, and zx, T2G3 orbitals, and then they are, this is edge sharing. So for this one, so that means this actually you have a ferromagnetic direct exchange between x, y, and the couple orbital, but you have antiferromagnetic super exchange between the couple x, y minus y and the iridium y, z, and the zx orbital. Okay. So now in the normal 3D and 5D materials, so there are competition between the ferromagnetic and antiferromagnetic interactions. So whether the system is ferromagnetic or antiferromagnetic depending on their relative strengths. But here, so why the system is ferromagnetic here, and also this displays strong ferromagnetic anisotropy. It is because here the iridium pseudospin has the internal structure. See, the real spin on the xy orbital is opposite to the real spin on the other 2 orbitals. So then you can see this one is ferromagnetic coupling, so they are perfect. And also this antiferromagnetic coupling also perfect. So there's no competition. They are cooperative. So this generates a large ferromagnetic interaction in the system. Then how about the spin excitation gap? That's coming from the anisotropy, because when you try to flip a pseudo spin, actually you change the LZ, the orbital magnetic moment along the z direction by plus or minus 2. But this in the real spin interaction, this operator actually preserve LZ. So that means the pseudo spin flipping is prohibited. So when the flipping process is prohibited, this will generate a large antiferromagnetic, it will generate a ferromagnetic icing-like anisotropy. But this ferromagnetic icing-like anisotropy comes from the original antiferromagnetic superexchange. So if we project out the lower light, the total angular momentum with 3/2 states, so we'll get the effective spin half spin is on the couple side, and the pseudo spin half on the iridium side. And this gamma 2 is the anisotropy parameter. So we can solve the Hamiltonian, and we can get the spin excitation spectrum and compare with the Rick's experiment. So we can find that this number is 2.6, so it's quite strong. Then, yeah, we can see calculated the lambda G factors for this material. What's interesting is that actually we get the iridium is negative, it's a -3. Okay, and the copper, that's a real spin one, so it's 2. So we have a staggered G factor. So this staggered G factor, so that's why give a small saturation to magnetization. That's the reason why it's a ferromagnetic, but its saturation magnetization moment is very small. And also, yeah, this one, that means also if you apply a magnetic field, a uniform magnetic field on a ferromagnet, but it will introduce actually the antiferromagnetic ordering of the spin and pseudo spins. So this will generate some strange state, like on the iridium side, it is fully frozen, but on the couple side, it is become fully random. Okay, yeah, I think I do not have time. Yeah, really have time for this material.
You have about 1 minute.
Yeah, this is a two-layer material. So, but in short, undoped material has an easy plane anisotropy. But when you doped with the ruthenium, it actually will introduce spin flop transition. Yeah, why it is happened is that because the material. Okay, I do not have time to delete for this. Okay, right now, yeah, I just show that. Yeah, we have shown several mechanisms, normal mechanism, magnetism in this 2 class of mixed 3D 5D compounds, and this magnetism are symmetry based and expected to appear in other 3D 5D materials such as the heterostructures. Okay, we thank our experimental collaborators to have verified our results, and these are the relevant publications. Thank you for your attention.
Thank you, Wei Guo. Do we have a very quick question? Since
Yes,
we have not have question. Okay, so if not, we'll just move on to our next speaker. Our next speaker is Wajzada Farouk. I hope I pronounce your name correctly. So you can.
Azizada Aslam, yeah. Yeah, okay, thank you very much.
Yeah. Go ahead and share your screen. Yep, we see a screen.
Yeah, can you see that?
Yeah, and you need to go to the presentation mode. Yeah. Great.
Okay, so thank you very much for giving the opportunity for all the committee members. So I'll be talking today on non-linear optical properties of nanostructured titanium dioxide embedded PMMA polymer using the Z-scan technique. My co-researcher are Nafisa Yaqub and Muhammad Al-Saleh. I'm from Department of Physics and Astronomy, College of Science, King Saud University, Riyadh, Saudi Arabia. Here is my contact email if anybody wants to discuss anything. So here is the outline of my talk. I will first introduce my research and then show the objective. I have used Z-scan technique to do this research. I will put some light on it, and then we'll explain the preparation of my sample. Then give the results obtained from in this research, and then I will conclude my talk. So at low light intensities, the properties of most optical materials are independent of intensity of illumination. However, if the intensity of illumination gets high enough, nonlinear optical effects can occur and the optical properties become intensity dependent. In the presence of illumination, the electric charges in the lattice of the material become polarized and form electric dipoles. The positive ion core does not move, but the electrons are displaced in a harmonic motion. The polarization is given by this equation, P equals epsilon naught chi E, where epsilon naught is the permittivity and the chi is the susceptibility. When the intensity of illumination is high, the electrostatic limit of the electron displacement is exceeded and the harmonic restoring force becomes nonlinear, which added quadratic and higher terms in this formula of polarization. And these terms are responsible for the nonlinear effect. So intensity dependent refractive index is given by this equation. Such materials have an ability of self-focusing or defocusing through their light intensity dependence on refractive index. So the nonlinear optical material exhibit interesting phenomena such as second harmonic generation, some difference frequency mixing, optical parameter amplification, wave mixing, and can be used for optical computing, switching, data storage, and parametric oscillators. The aim of this project is to synthesize a material with a low absorption coefficient, low cost, flexible, good stability in the environment, high optical damage threshold, ultra fast response with better processing ability and ease of fabrication and harmless to the environment. So there are many methods to measure nonlinear optical constant, but we have used Z-scan technique. So in Z-scan technique, we use a laser to measure or to scan the transmission through this sample, which is moved from minus Z to plus Z through the Rayleigh length. The Rayleigh length is given by this formula, where omega naught is the waste of the laser beam. In order to reduce the laser fluctuation, we divide this beam into two parts. One is used as the reference, and the other one is used to detect the transmission through the sample with a detector. So Z-scan is divided in two parts. One is open aperture and the other one is the close aperture. In open aperture, we scan the whole beam after transmission through the sample, while the sample moves from minus Z to plus Z, and this scan is used to calculate the nonlinear absorption coefficient. As you can see here, the profile of the absorption. In close aperture, we scan only the inner part of the beam, and this actually recorded the refraction of the light passes through the sample. Again, the sample moves from minus Z to plus Z through the Rayleigh length. So the thin film was prepared using solvent caustic method. The powder was dissolved in the chloroform at room temperature, stirred by the magnetic stirrer for 1 hour to dissolve to dissolve to make a homogeneous solution. Then different concentration of titanium dioxide nanoparticles were added to make different samples. The polymer composite solution was then placed for 20 minutes in the ultrasonification, then again put into the magnetic starter for 1 to 2 hours until the homogeneous dispersion was obtained. So resulting solution were then poured into separate Petri dishes and left to dry for 2 days. So here you can see the XRD pattern of titanium dioxide and the polymer. You can see here polymer is very little peak of 101 is of titanium dioxide is appearing, which shows that the nanoparticles are present in the sample in a very low quantity. So here you can see the SEM of these all 6 samples, and in the figure F we can see this distribution of these sample, because this sample has a very high concentration of titanium dioxide nanoparticles. So we have measured nonlinear absorption coefficient, nonlinear refractor indices, and third order nonlinear susceptibility using Z-scan and Z-scan profiles with CW laser of wavelength 532 nanometer. So here are the profile of open aperture Z-scan. These are taken at different laser output power and are used in the calculation of nonlinear absorption coefficients. And these are some profiles from close aperture Z-scan, and these are used to calculate the nonlinear refractor indices. These are actually the profile of refraction from the close aperture Z-scan. So the dependence of nonlinear absorption coefficient and nonlinear refractor indices on the laser output power are shown in this figure. We can see here the variation of absorption coefficient for different concentration of nanoparticle in the sample at different powers output of the laser, which varies from 20 to 100. So we can see here the most nonlinear effect is observed in the concentration of 0.24 watt percentage anatase nanoparticles, and these are the result of the nonlinear refractor indices of the same samples of different concentration at different laser output powers. So these are the formulas which we have used to calculate these points in the graphs. So third order nonlinear susceptibility, optical susceptibility, is calculated from open and closed Z-scan data, where nonlinear refractor index is related to the real part, while the nonlinear absorption coefficient is related to the imaginary part of the Sky3 through the relations. So these relations are used to calculate the third order nonlinear susceptibility, and these 2 columns, we have given the data in these 2 columns which present the third order non-susceptibility. So we have concluded that the polymer PMA with anatase nanoparticle have a positive non-linear reflector index. The nonlinear absorption coefficient of this PMA and titanium dioxide nanoparticle anatase phase is in the order of 10 to the power -2 centimeter per watt. Third order nonlinear optical susceptibility of these samples are in order of 10 to the power -6 ESU. Thank you very much. If there's any question, you can ask, please.
Thank you. Great. So questions? You could unmute yourself and speak out directly. Our audience has been quiet. Okay, so if no questions for now. Again, our speakers' emails are all available online. So let's move on to our next speaker. Our next speaker is Arif Hassan Da. Arif, are you here? Oh, okay. Let me see.
Hello, doctor. We have video for Dr. Arif.
Yeah.
So we can play that video.
I have those all downloaded. Let me see which one. Access to presence. Okay, so I will play the video of the submitted talk.
Good morning, all. Myself, Arif Hassan.
Hold on. Okay. To ship, let me. Share screen. Screen two. Yeah. I will play this for 10 minutes because you will have access to those recorded video online this whole week. And I will stop at the stopping time, even if it's not finished. Okay. Oh, I think I need to choose the share sound. Yeah.
Good morning, all. Myself, Arif Hassan. I will give a presentation on access to fluorescent organic push-pull chromophores with white light emitting property containing urea as an electron donor. I completed my PhD under the supervision of Dr. Jamrun Govindasamy at Institute of Nanosciences and Technology, India. Before going into the main topic of my presentation, I will give a brief introduction about the non-polar organic push-pull chromophores. Push-pull chromophores are simple molecules with a end group containing a donor and the acceptor parts. I suppose here, if you can see, it's one of the donor molecule, imine end is the acceptor molecule, and in between these two donor acceptor molecule functional groups, there is the presence of conjugation. So basically, the presence of the position and the presence of donor and acceptor groups with the conjugation amount, extent of conjugation, the properties of molecule will get changed. Suppose if we have a conjugation, longer conjugation, then we can have an absorption spectra in towards a lower wavelength region, and if we have a less conjugation between the donor and acceptor parts, we will have a absorption towards a longer wavelength region. This is just a simple example here. This graph, you can see the position of the donor and acceptor groups has a huge impact towards the absorption spectra of the molecule. Basically, this Dilthey and Witzinger came with the theory of oxochrome chromophore theory. They said that chromophores are electron withdrawing groups and oxochromes are electron donating groups. Since the donor acceptor molecules are blurred, it's because of the presence of newly formed homolumo orbitals, which lie whose electronic shift lie in the region of visible region of spectra. That's why they are colored. So this is just one of the examples I showed here, the hemoglobin, in which you can see the presence of difference between the presence of two oxochromic groups like methyl and the aldehydic group has a huge impact in its absorption spectrum. But the question is, why do we care about the functional groups or the donor or the acceptor groups present in a molecule? Since we know that different functional groups, different donor functional groups and different acceptor functional groups have different Hammett constant values, which is a response, which is the parameter which has been set by the physical organic chemists for determining the reactivity of different organic molecules. Here you can see that the nitro group has a Hammett para substituted Hammett constant value of 0.78, and NME2 group has an para substitution Hammett constant value of minus 0.83, which is the highest known value for the reactivity in terms of its reaction in cycloaddition reactions. So Why do we care? The question again remains the same. In 1974, Avram and Ratner actually did a groundbreaking work, which is a highly cited paper in this physical chemical Arterials paper. They synthesized a molecule, organic molecule rectifier. From that time, there's a huge transformation in organic electronics, because the molecule which they had synthesized has a huge scope in determining advanced functional materials, like it has a tunability in hemolimo gaps and soft materials. It was soft material, the device fabrication was easy. After that, there has been a tremendous shift in research towards organic electronic materials. But what we did is we used 2+2 cycle addition retroelectrocyclization reaction between the donor substituted alkyne and the acceptor substituted alkene. As this is just a general synthetic protocol for the synthesis of non-pure push-pull chromophore, which we followed. Here you can see that the alkyne, this is the alkyne with the donor substitution, and this is the acceptor with the alkene. They will undergo 2+2 cycle addition by this alkyne and this alkene, and will form butadiene system, and then it will undergo retroelectrocyclization with the formation of push-pull system with a completely different dihedral angles. These are some of the donor molecules. The silent features of this reaction were this is just first a single step click type reaction. The product formed is a twisted non-pure push-pull chromophore, and the product has an efficient charge transfer, and the molecule is completely stable. So these are some of the donor blue colored are some of the donor molecules which are present in literature, and these are some of the acceptor molecules which are also present in literature. So these are some of the additions in the library of donor and acceptor parts which we added by my research, by my PhD thesis. This is the urea which we added in the donor part, and this is the acceptor which we added in the acceptor part. These are some of the push-pull chromophore system which has been reported from the last decade by Dietrich group. So what we did is, since all these push-pull chromophoric system has some limitations and some properties too. So the inherent properties of the push-pull system, which has been already known, is they have stable, they have redox behavior, reversible redox behavior, they have the stronger ICT band, and but the limitation of them was they were fluorescent. There was not any kind of functional group modification of their formation. But we come up with a urea. Urea, we suppose, is a molecule which consists of a nitrogen containing lone pair of electrons. We thought that if we can make a molecule of urea with an alkyne substitution, then if we bring the alkene with an acceptor functionality close to alkyne, then it may undergo 2+2 cycle addition reaction, and it may result in the formation of push-pull chromophoric system. The main merits of this were we can have a functional group modification, and the presence of hydrogen bonding in urea may evolve its applied material properties. So what we did is, the hypothesis was, since these two nitrogen has urea has 2 nitrogen atoms with 2 hydrogens and 2 lone pair of electrons. So at one point, since this carbonyl group is in complete resonance with both of these lone pair electrons, we feel that if we have on one side alkyne, the main objective is to make alkyne electron rich. So what we see is we feel that if we bring somehow alkene close to this alkyne, at that time this one of lone pair electron will be in resonance with this, and this will be in resonance with this alkyne. And if we bring close this acceptor molecule to this, then it will have a 2+ cycle addition reaction. So actually this works, and we synthesize these 3 molecules by using the same procedure, and compare the properties of these 3 molecules with the reference molecule which has been synthesized proven in 2005. After the synthesis, after the rigorous synthesis, we check its photophysical properties. This is the UV visible spectra of this molecule. This blue,
this video is more than 14 minutes long, and we're not going to wait until the end. Let me see whether I can drag directly through to the conclusion for now, because let me see. And again,
we collaborated with one of our
all these
you
recorded videos
check
will
whether the
be
molecule is
online
biocompatible
available
or
if you
not,
want to check.
and which is the follow-up my work. Thank you. I would like to acknowledge my supervisor, Dr. Jamurgan, without whom the work would not have been possible. This is our lab. Thank you.
Okay, so since the speaker is not here, let's continue to our next talk. This is totally messed up. Where's my screen? Okay, so our next speaker is Nadia Kukta. Is our speaker here? Is our speaker here again? Okay. I'll play the recorded video again.
Hello, everyone.
Share screen. Share sound. Okay.
Hello, everyone. My name is Nadia Kukta. I'm currently a postdoctoral researcher at the University of Washington in Seattle. However, today I'm going to present to you the work which I did during my previous employment at Durham University in the UK. For more than 10 years, I have been working in the field of organic semiconductors, and I particularly enjoy working with emissive organic semiconductors. Therefore, my today's work is dedicated to a special case of emissive organic semiconductors pairing room temperature phosphorescence and thermally activated delayed fluorescence phenomena. Fluorescent organic semiconductors can find their applications in organic light-emitting diodes, or OLED in short, which moved rapidly from the lab benches to industry. Then go sensors, biorecognition, and as we all are concerned about privacy, security inks, and anti-counterfeiting. For example, organic light-emitting diodes are multi-layered devices consisting of two substrates, two electrodes, hole and electron injecting and blocking layers, and the emissive layer on the development of which my work is focused. The materials for anti-counterfeiting and security inks tend to utilize a little bit more complicated properties such as afterglow and stimuli response. Here you can see the requirements to the emissive compounds. First of all, this is stability, means thermal and electrochemical stability, the emission color controlled by the wavelength, and most importantly, the emission intensity. However, fluorescent emitters tend to utilize only singlet states, and that leads to only 25% internal efficiency in the LEDs. The question is, why not to utilize triplets then? Charge recombination in organic light-emitting diodes gives 25% of singlets and 75% of triplets. Triplets are generally non-emissive at room temperature. The utilization of heavy metals such as iridium and platinum induce mixing of singlet and triplet states by spin-orbit coupling. However, this kind of complexes tend to be unstable and the metals are expensive and toxic. In turn, the DDF tends to harvest triplet states by reversing the resistant crossing, thus leading to 100% efficiency. Currently, there are two ways of triplet harvesting on the peak of research. This is room temperature phosphorescence and thermally activated delayed fluorescence. TADF upconverts triplet energy to singlets, thus leading to the enhanced emission from singlet states. That finds applications in organic light-emitting diodes, sensors, and bioimaging. On the other hand, RTP utilizes the emission from usually non-radiated triplets. And here I should say that it is quite uncommon to observe room temperature phosphorescence, as the majority of organic compounds tend to exhibit their phosphorescence only in rigid media and at low temperatures. Thus, the applications of RTP are bioimaging and security inks. And while these two processes are quite fundamentally different, the materials share quite a surprisingly similar design. Speaking about the molecular design rules for the TDF emitters have been polished throughout the years. However, here you can see one of the most common molecular designs utilizing rigid donor, rigid acceptor linked covalently by the nitrogen-carbon bond. We have to ensure a tiny rocking of the donor acceptor to have the radiative decay. Also, donor and acceptor unions have to be balanced, and their HOMO and LUMA have to be separated, though showing a tiny overlap to ensure good optical properties. Also, we are looking for a small delta AST to enable an efficient risk from triplet to singlet state and high fluorescence quantum yield. Key signatures of the TDF process include the charge transfer nature of emission, the ratio of the late fluorescence to prompt fluorescence increases at higher temperatures, the addition of oxygen tends to quench triplets, and most importantly, we are looking for the linear dependence of the late emission with laser power to distinguish from the triplet-triplet annihilation process. Current challenges include understanding the complex interplay of steric effects, small singlet-triplet energy gap, charge transfer state, vibronic decoupling, then also looking and designing for new structures, enhancing the LED efficiency and color purity, and trying to increase the rate of reverse intersystem crossing. So how is RDP different? In terms of the molecular design, we are still looking for the orthogonally linked donor and acceptor structure. However, we want to incorporate the heteroatoms to favor internal system crossing because this is what exactly leads to the RDP emission. Also, we are looking for the rigid triplet first triplet state with a hybrid pi-pi and pi character, and preferably one conformation of the molecule in both ground and excited states. Here you can see the advantages of RDP, such as tunability by molecular design, thermal and electrochemical stability, and practical applications can be enabled by casting from solution, gel, and processing from solid powders and crystals. Current challenges are similar to those of TDF, such as understanding the complex interplay of steric effects, also increasing the phosphorescence lifetime, and looking for blue phosphorescence. Therefore, in this work, I want to show to you how by simple modification of the molecular design, it is possible to ensure efficient TDF and also increase the efficiency of RDP. As we remember, the main requirements for TDF and RDP emitters include perpendicular donor acceptor architecture, decoupled donor and acceptor, and sufficient charge transfer character. However, if we take a small donor such as carpazole and link it orthogonally to the acceptor, we will not be able to ensure orthogonal orientation because the donor does not provide sufficient steric hindrance and it would rotate freely around the donor acceptor bond. That would lead to the lack of charge transfer character and cancel TDF in this case. Therefore, to ensure strong charge transfer, we tend to utilize six-membered ring donors such as phenothiazine and acridine. While those enable stronger charge transfer character, they might also lead to the observation of various radiative and non-radiative pathways. For example, as you can see here, linking phenothiazine donors orthogonally to the plane of the acceptor leads to TDF in a so-called equatorial conformer, while attaching the donor in one plane to the acceptor leads to the axial conformer, which shows RDP and no TDF. Therefore, in this work, we have designed and prepared three materials, wherein xanthine acceptor and phenothiazine donors. We have attached bulky terbutyl groups to ensure steric hindrance and to lock the compounds in solely one conformations. We wanted to get equatorial conformation, and we have linked the phenothiazine donors in meta and ortho positions to the sulfur of the acceptor. Additionally, by swapping the terbutyl by the bulkier electron-accepting benzoyl group, we were able to enable TDF in this molecule. To check whether we are ending up having stable equatorial conformations as we wanted, we ran ground state DFT calculations, and here you can see the energy scans proving to you the stability of the equatorial conformer. Thus, we can see that the barrier needed to twist the molecule by a certain degree, for example, like 20, 40, 60 degrees angle, is quite high. This is a direct proof of the stability of the equatorial conformation which is the highest in the benzyl substituted compound. Further on, we proceeded with computing the first singlet state properties. And the main takeaway message from this slide is good separation of HOMO and LUMA in the benzoyl substituted compound, which we are looking for the TDF material, and a little bit larger charge transfer character in the ortho substituted terbutylated material. Here we can see the singlet and triplet energy diagram of these compounds, and as expected, both terbutylated compounds show a
Again, this video is much longer than 10 minutes. We're not going to finish this anyway, so I will see whether there is a conclusion slide.
One equatorial conformation, but also we were able to contribute to the existing design rules of this molecule. Thus, for the efficient RDT emitters, we are looking preferably for a singular conformation and a rigid geometry in the T1 state with a certain degree of charge transfer, while for the efficient ADF compounds, it is useful to use the carbonyl group to promote the reverse intersystem crossing and rigid skeleton. Thank you for your attention.
Okay, we'll move on to our next speaker. Let's see. So our next speaker is Hanadi Brace. Hanadi Brace, are you here? Or okay. Oh, let's see. Share screen. I'll play the pre-recorded video again, and we will stop whenever the time. I'm counting my time here. And again, all the videos, pre-recorded videos, are available online if you want to check.
Introduce myself. I'm Ratiba Benzalga from ATL Lab, University of Rennes. I'm going to present you today our work on long carbon fibers loaded ultraporous epoxy composite for planar microwave absorber materials. Here is the outline of my presentation. First, I will present the context of this study by presenting the commercial absorber material and our proposed material. Then, in the second part, I will present the multi-layer absorber, starting with the elaboration method, then the influence of the elaboration parameter on the morphological structure, then the prototype achievement and characterization result. I will finish my presentation with the conclusion and perspective. Let's start with the context of our study. I start with this simple presentation of absorption principle. When an incident electromagnetic wave arrives on the surface of material, a part of this wave is reflected, a part is absorbed, and the last part is transmitted through the material. In the case of absorbing material, we need a low reflection, a low transmission, and a high absorption of the electromagnetic waves. The form and composition of the absorbers are various and depend on the targeted application. For the composition, we can find the magnetic or dielectric absorbers. In our case, we deal with this last type of absorbers, and we are looking for low permittivity in order to reduce the reflection, and high dielectric losses for a high absorption and thus a low transmission. Absorbing materials are used in several fields of application, for example, stealth, in antennas, and for the protection of microwave circuits, and they are also used to realize anechoic chambers. Our targeted application here is the anechoic chamber. In this chamber, absorbing materials with probe and absorption are used. The thick absorbers are often needed to obtain broadened absorbers. For these absorbers, it is necessary to ensure a gradient of impedance to minimize the reflection of the waves at the interface air absorber. For this, we can use a physical gradient where the gradual impedance is obtained by varying the geometry of the material itself, or a gradient of properties by varying the composition of each layer, which is the case of multi-layer absorber. In this work, I will present this type of absorber. Today, absorbers used in the anechoic chamber are often as a form of pyramidal or multi-layers made of polyurethane foams loaded with carbon nanoparticles. The advantage of these absorbers are their low density, which facilitates their installation in the anechoic chamber, and their low carbon particles, which ensures a good absorption performance in wide frequency range. In addition, the frequency range and the performance of these absorbers can be adapted by varying the carbon content and dimensions of these absorbers. On the other hand, these absorbers have some disadvantage. First, the used loss, which is a volatile escape from the matrix and induces a numeric pollution and the premature aging of this absorber. And the second one, the flexibility of this absorber increases machining errors and prevent the realization of complex shape that can increase its absorption performance. In order to overcome the limitation of commercial materials, we propose to study new absorbing materials based on epoxy foam loaded with long carbon fiber. Here, the rigid foam permits the achievement of new and complex geometry for the optimization of absorption performance. This aspect is treated in my presentation on Friday at 9:15 a.m. On the other hand, carbon fibers are non-volatile load and their use guarantee good performance over time. But this proposed material presents high density, about 0.14 gram per centimeter cube, compared to commercial absorber with density of 0.07 gram per centimeter cube. So the objective of this work is to reduce the density of this composite, also to reduce the thickness of these absorbers, and to use a low amount of load, keeping the same absorption performance. So this is the topic of the second part of my presentation. I present here the elaboration method of the ultralight epoxy foam. First, we start with the pre-dispersion of carbon fibers of 12 millimeter length. These fibers are added to solution of acetone and SDS, which is a chemical dispersant, after which ultrasound is applied to disperse these fibers. Then the dispersed fibers are added to the epoxy resin. The whole mixture is put in the oven to evaporate the amount of acetone and to leave only the desired amount of acetone in the mixture. Then the foaming agent is added and mixed with the spatula, and this mixture is left at room temperature for 6 hours to finalize the foaming steps, then at 60 degrees to finalize the polymerization. Finally, the foam will be cut to be characterized. Now I will present the effluence of the acetone amount left in the resin on the structure of the foams. We can see clearly on this photo that the volume of the epoxy foam increases when the amount of the acetone increases to 15%. After that, the limit is reached at 20% of acetone. The optical and the same images shows that the size of pores of epoxy foam increases when the amount of acetone increases. By varying acetone amount, we succeed to reduce the density from 0.14 for epoxy without acetone to 0.05 by using 15% of acetone. After this amount, the density increases because the foam structure is altered. In this part, I present the ultralight foam with 8% of acetone loaded with 0.075% of carbon fiber. compared to the standard form without acetone. Here are the photos and the dielectric properties of these two samples in the frequency band between 2 and 18 gigahertz. Results show that the real permittivity of sample with 8% of acetone decreases when the acetone is used. This decrease in permittivity increases the impedance matching between the air and the absorber and interface. At the same time, we keep the same losses, which is ideal to realize an absorber material. Here I present also the dielectric properties of 5 symbols loaded with different concentration of carbon fibers from 0.0125% to 0.075% of carbon fiber. We observe that the permittivities of sample are very close to the permittivity of air, which increase the impedance matching between the air and the absorber. On the other hand, we observe that the losses increases when the concentration of carbon fiber increases. We notice also that the samples show a gradient of losses, which allow us to realize a multi-layer with an impedance gradient. The simulation of the absorption performance was first done using the CST software and the presented dielectric properties, and the thickness for this simulation is 125 millimeters. This thickness is chosen because it is often used for commercial multi-layer absorbers. This simulation predicts a good absorption performance with a reflection coefficient lower than -13 dB in all the studied frequency range, which means that more than 95% of acetate waves are absorbed. The multi-layer prototype is carried out with these 5 layers, and the measurement of this prototype is done and compared to the simulation and the measurement of commercial absorber. First, we can notice that the measurement of the realized prototype shows a reflection coefficient curve quite similar to the simulated one. Moreover, the absorption performance of our prototype is very close to the performance of the commercial material and slightly better at some frequencies, especially at high frequencies. One can note here that our prototype is very lightly loaded compared to the commercial one, as we can see on these photos. Now I will show you the result of another lightweight and optimized prototype using a program that we developed. This program uses the genetic algorithm optimizer. The new prototype is made with 3 layers and has a total thickness of 90 millimeters. This prototype will be compared to the epoxy prototype and to the commercial absorber with 125 millimeter thickness. In order to better compare this prototype by taking into account their reflection coefficients and their thicknesses, factor of merit was calculated using this formula. Here, this factor is inversely proportional to the linear measured reflection coefficient and to the thickness of the absorber, because we are trying to reduce these 2 parameters. From these 3 foam curves, we can say that at low frequencies we obtain better performance for the epoxy prototype with 125 millimeters, here the blue curve, and at high frequencies the better performance is obtained with the epoxy prototype of 90 millimeter thicknesses, here in a green curve. Now, if we compare our second prototype with the low thicknesses, with the commercial material, we can say that we obtain comparable performance at low frequencies, even better at high frequencies with our prototype compared to the commercial one. Here is my conclusion. I let you read it, and before finishing, I would like to thank Jérôme Sol for his technical support and all the different organizations for their financial support.
So I decided to finish this video because we don't have our next speaker here, and we don't have the pre-recorded video. To stick with the schedule, we'll wait for 3 minutes until 2:20 before we move on to our next speaker. And I would like to ask, is our next, oh, I see you. Okay, great. So we could start after 3 minutes. So we will be with the original schedule then. Our next speaker is George Andres Guerra Torres. I see you in the audience. Yeah. Hi.
Hello. Yes, I'm here.
Yeah.
Do you mind if you can play the video for me, please? I'm unable to.
You want me to
leave
play the
right
video?
now.
Yeah.
Yes,
I
please.
do have
Thank you.
your video.
Hello, everyone. My name is
So since your video is a minute and a half longer, so maybe I could just start playing now.
Yes, thank you very much, Chair.
Sure. So screen share. Okay.
Hello, everyone. My name is Andres Guerra. I work in the Catholic University of Peru. And today I will be presenting our results concerning the luminescence activation of terbium-doped ITO thin films and their impact on the host optical and electrical properties. Our interest in introducing rare earths in TCLs is to introduce a new additional property, luminescence, to an already multifunctional material without compromising their optical transparency and electrical conductivity. We believe that this might open a wide range of applications in light-emitting devices, in solar cells as downshift and up-down conversion layer systems, as well as gas sensors. We have grown our samples by radio frequency magnetron sputtering in a way that we are able to obtain samples with different terbium concentrations in a single deposition process. Additionally, we realized by experimentation that in order to activate the terbium-related luminescence by post-deposition thermal treatments, it was necessary to cool down the substrates during the deposition process. We performed this using a closed-cycle cooling system and put the temperature of the substrate down to 10 degrees Celsius. Also, we study and characterize ITO films without any terbium grown in a similar fashion. If you're interested in details concerning these results, please visit the abstract ID and the work presented by Miguel Piñeiro. Here I'm showing you the elemental concentration versus the terbium concentration of the samples we have grown. And we will be focusing on these samples between this concentration range for this concentration range of terbium, due to the fact that for higher concentrations we will have the concentration quenching effect of the luminescence. After deposition, ITO films grown under these conditions exhibit a polycrystalline structure, whilst ITO doped with terbium exhibit an amorphous structure. After annealing, ITO films increase their grain size, whilst the terbium-doped version crystallized. We were able to obtain the luminescence from the terbium ions embedded in this host by post-deposition thermal treatments and under this excitation wavelength. Here I'm showing you the luminescence spectra for 3 different annealing temperatures of a sample with 1.5 atomic percent of terbium. We are able to identify the typical electronic transitions related to the terbium ions. And interestingly, we see that the 5D4 to 7F2 transition increases in intensity for this annealing temperature. This is quite an unexpected behavior. Concerning the interacted emission intensity, we see that the emission intensity associated to terbium increases with annealing temperature till certain temperature, and then it decreases again. A similar behavior is observed for the host-related emission of the same sample. We believe that this variation here is associated to an effective competition between the recombination and subsequent energy transfer to host-related states and terbium states. We believe this because when we monitor the emission of an undoped ITO sample, we see that the host emission increases with the annealing temperature, meaning that we might be activating other recombination paths and luminescence centers associated to the host. For comparison purposes, I'm showing you here the color or the apparent color in this color space, CA1931. And we see that for higher annealing temperatures, there is a shift to the red, which is, again, unexpected for terbium ions. Concerning the concentration quenching effect I mentioned earlier, here I'm showing you the luminescence spectra for samples annealed at 550 degrees and for different terbium concentrations. If we look at the integrated intensity, we see that, in fact, after a concentration above 2.3 atomic percent of terbium, the emission intensity is quenched dramatically. This is known as the concentration quenching effect. In order to probe the potential excitation mechanisms between the host or any transfer mechanism between the host and the terbium ions, we perform thermal temperature-dependent photoluminescence measurements on a sample grown with 1.5 atomic percent terbium and annealed at 550 degrees Celsius. So here I'm showing you the emission intensity versus wavelength for different sample temperatures. And on the right, I'm showing you the integrated emission intensity associated to terbium and associated to the host. We see that when we increase the sample temperature, we lose terbium emission and enhance the host emission. From this data, we perform an Arrhenius plot, and we are able to identify two activation energies associated to the thermal quenching process. So we believe that the excitation mechanism or energy transfer mechanism from the host to the rare earth takes place by the formation of bound excitons to rare earth structure isovalent traps. So after excitation and the formation of an electron hole pair, the electron hole pair will form an exciton bound to rare earth or rare earth cluster, because these rare earths can form clusters of 2, 3, or higher dimension or higher sizes. These clusters will create a potential that will attract holes or excitons, and they will be bound to this potential. So after recombination or the annihilation of this exciton, energy will be transferred to the rare earth, and therefore the rare earth is excited to a higher level. So there are two models to treat these rare structure isovalent traps. One is the Koster-Slater model, and the other one is the spherical potential well model. We have used these two models and the activation energies we obtained earlier to calculate and predict other activation energies or binding energies, assuming that these activation energies are actually the binding energies of these excitons to these rare isovalent traps. Unfortunately, we were able only to measure two activation energies, and from them we calculate the binding energies for clusters of larger sizes. Our results suggest, or the results obtained from both models, Koster-Slater and spherical potential, are in agreement to what we actually could expect from this material. However, we're still studying and trying to find if we can measure additional activation energies, which can perhaps match the calculated ones. In fact, there is another work we are presenting in this conference by Paul John Top on terbium doped aluminum zinc oxide, in which there we were able to identify 4 activation energies, and they match pretty well with the theory. So concerning the optical properties, we measure the optical bandgap and Urbach energy, and in this plot I'm just relating them. So here we have bandgap versus the Urbach energy for samples with different terbium concentrations, samples with terbium concentration but for different annealing treatments, and samples without any terbium but for different annealing treatments. And we observe the same trend. The bandgap increases when we increase the Urbach energy. We believe that this relation is actually associated to the fact that when we introduce terbium ions, for instance, or when we perform annealing treatments to the sample, we activate charge defects like oxygen vacancies, among others. And therefore, we increase the bandgap by means of the optical bandgap by means of the bursting Mohs shift. So when we activate these charge defects, or we form new defects by annealing treatments or the inclusion of terbium ions in the host, we are also increasing the Urbach energy of the system. Also, we perform 4 probe measurements or Van der Pol measurements on samples with no thermal treatment, but for different terbium concentrations. And we see that for a small amount, of course, we observe resistivity larger to the typical resistivity one obtains on ITO, in particular due to the grow conditions. We grow these samples by cooling down the substrate holder. But very interestingly, we see also, in agreement with the optical analysis, that for small amounts of terbium in the host, there is a reduction of the electrical resistivity. Here on the right, I'm showing you the electrical resistivity of a sample with 2.3 atomic percent of terbium versus the annealing temperature. And on the red curve, I'm showing you the evolution of the electrical resistivity with annealing temperature of a sample without any terbium, grown on similar conditions. So again, if you're interested in checking the optical properties and electronic properties of ITO grown under these conditions, you can check this work. And if you're interested on learning about the energy transfer mechanisms in terbium doped aluminum zinc oxide films, you can check this other work, which is also presented in this conference. So thank you very, very much for your time and for this opportunity.
Okay, thank you. We actually have the speaker here if there is a quick question. If not, I believe we have our next speaker, Miguel Pinerio. Miguel, are you here? I think I see you.
Hello, Mr. Yang, I hear.
Yeah.
Can
you
play
go ahead and share your screen?
My presentation, please? I don't.
Oh.
I can't speak.
Okay. Yeah, sure. I have everything downloaded and prepared. Okay.
My name is Miguel. I am master student.
Hold up. Share screen.
My name is Miguel. I am master student in the Pontificia Universidad Católica del Perú under supervision of Professor Jorge Guerra. And today I will talk about optical and electrical properties analysis of spattered ETO thin field taking into account ground-induced inhomogeneities. So, ETO are the most intensively studied semiconductor because they show high transmittance in the visible region and low electrical resistance. This low electrical resistivity of ETO is due to a higher carrier concentration because the Fermi level in the energy band diagram is located above the conduction level. This degeneracy is caused by substitutional team who occupy indium sites. This affects a distortion of the Bix-by structure and allow the formation of oxygen vacancy. These defects, institutional team and oxygen vacancy, contribute charge carrier in the conduction band and explain the good conductivity. Due to these properties, they are used in display device, but these properties are affected by complicated microstructure creating during the field deposition and post-deposition annealing. Because of this, we prepare ito layers at low substrate temperature in order to induce inhomogeneity microstructure and tuning the optical and electrical properties. So, how we fabricate these materials? We prepare ito thin fields by radio frequency magnetron sputtering with substrate cooling active during the deposition process without rotating in order to have various samples with different thickness. Using EDS spectroscopy, we obtain the elemental composition, and we can see in this figure the elemental composition don't change with increasing the thickness. Then thermal annealing is done at different atmospheres such as air or argon in order to modify the optoelectronic properties. First, we need to know how does the microstructure of ito behave. In this figure, show the XRD pattern of ito thin fields at different annealing temperatures at argon atmosphere, where we can see ito as ground present an amorphous structure, and as we increase the annealing temperature, the field is more crystallized. So we know the first nanometers of thickness of the ito field grow in a disordered way, while the following nanometer have a columnar ground as shown in this figure. Due to complicated ground, we separate the ito field into two layers. This figure is from this reference. Now I will show the main result. We measure the optical transmittance to ito sample at different annealing temperatures, air and argon, where can see ito sample at air atmosphere don't present a change significant in the transmittance in compared with ito sample at argon atmosphere. I mean, the transmittance in the infrared region decrease and the edge absorption toward higher energy. Well, these two layers are also known as gradic layer model. Typically, the electrical function modeling of ito is performed by using the Drude model and Tau-Lorentz model, considering only a single layer. But in this study, we model like two layers. Both layers share the same Tau-Lorentz parameters, but different Drude parameters in order to obtain different carrier density and mobility for each layer from transmittance measurement. Now, show the transmittance as a function in the wavelength, where the experiment data is small triangles and the solid line is the transmittance feed. The feed was obtained by using the previous model, the Drude model and Tau-Lorentz model, and we found that the behavior or carrier density divided by a constant error for both layers as of the annealing temperature. R is the equal band effect mass divided by mass. For the bottom layer, the blue graphic, the carrier density increased in constant with the top layer, which decreased, and this is due to the structure is being rearranged at the beginning of the temperature, and 150 degrees centigrade begin increasing in both cases, since the substitution of indium or by tin and the creation of oxygen vacancy may be occurring. So as the electrical current has a radial behavior. We will take the two layers as they were parallel resistors. In this way, we calculate the electrical resistivity for transmitter measurement and compare with the electrical resistivity measured by Van der Pol technique, as shown in this figure. We can see both resistivity present the same behavior. The log electrical resistivity value was obtained at 500 degrees centigrade. Now, in this figure, show the energy, the left figure, and the right figure is represent the Urbach energy. Both are as a function of the annealing temperature. They were calculated by using band fluctuation models. We can see in the left figure the widening of energy backgap can be by the boosters. It is related with increasing current density. Now, in the right figure, we can also confirm that the Urbach energy is increasing with annealing temperature. So we may expect the defects are increasing since the Urbach energy indicates us the disorder degree. The rest is a guide to the eye. To summarize this, using cooling active during fabrication on thin films is induced ground on inhomogeneity in microstructure in order to investigate the optical and electrical properties. Then layers model and optical measurements and determine density and mobility at different annealing temperatures at an argon atmosphere in order to investigate the electrical and optical properties. And that is reflected in the change of the electrical resistance. Finally, I want to thank institutions that funding this work: Fondesi, Concitec, Office of Naval Research, and Matter Group. Thanks.
Miguel is here, so I would ask for one last time because I don't think the next speaker is here. Any question for Miguel? Our speaker is here. Okay, if not, we'll have our last talk by Afrim Sahia. I don't think the speaker is here. I'll just go ahead and play the video. Oh, hi. So I'm going to share my screen. And this video, I see it's half an hour. So I will stop at 2:50 because we're not going to play the half-hour video for a 10 minutes talk. Okay. Share screen. Again, I'm going to stop at 2:50 to conclude our symposium.
Hi. Okay, let me get it. And ladies and gentlemen, I'm Efrem Su here, and the title of my presentation that will last a little bit, probably longer than 15 minutes, is Analytical Predictive Modeling in Design for Reliability of Electronic and Photonic Materials, Assemblies, Packages, and Systems. I will not read everything what you will see on the slides. You will read it to an extent possible. I will simply, my presentation will summarize the major messages that a particular slide contains. So this, the summary of my presentation is, I will focus on merit and attributes and challenges associated with analytical mathematical predictive modeling. And I will try to focus on the physics of what's going on, because analytical modeling has even an advantage over computer-aided modeling when it comes to understanding the physics of failure. I'll particularly cover 5 items, which are the interfacial thermal stresses. Everything is analytical / mathematical modeling. Thermal lattice mismatch stresses and their interaction. Dynamic response of electronic system to shocks and vibrations. Avoiding low cycle fatigue conditions. What could possibly be done to do that? And if all the measures will not be successful, at least the size of the inelastic zone will be minimized. And that will certainly improve the long-term reliability. And the last but not the least, they say failure-oriented accelerated testing in probabilistic design for reliability, because the truth of the matter is that there is no such thing that everything is ideally reliable or never fails. The difference, however, between a highly reliable and sufficiently reliable technology or structure is simply the level of the probability of never zero probability of failure. And I will conclude about, again, the role of analytical modeling. Actually, everything what I'm talking about has to do with a discipline that could be called structural analysis in microelectronics and photonics. And this is important to emphasize, because the structural analysis is partially due with material science, certainly, but more than that, with mechanical behavior of materials, and certainly in application to electrical and photonic engineering. So all these 3 items are important. So first, predictive modeling. That's important because I will not go to all these details, but I will only emphasize that it has to do with the future, has to do with thermal stress failures, has to do with dynamic response, has to do with probabilistic design for reliability. At Bell Labs, and I was with Bell Labs for 20 years in the basic research of Bell Labs, we used to say that you can have the best chip in the world, but if you put it in a piece of junk, which is called a substrate, you end up with a piece of junk. And that's why the mechanics of materials, with application to electrical performance or optical performance, is that the area to which my presentation belongs. Analytical modeling occupies a special place in the modeling effort, and I have to emphasize that because now everyone, including myself, we do finite element numerical modeling, but analytical modeling quite seldom could be used or should be used instead of finite element modeling, but typically should be used in addition. But for new structures where there is no accumulated experience yet and no specifically developed finite element procedures are available, analytical modeling helps a lot. Actually, when I use finite element, I apply analytical modeling to develop the pre-processing model that always helps. What I've been talking about is actually, of course, there are several books, and I'm either monographs or the only author, or I'm one of the editors of these books, where what I'm talking about will be described. Here's a typical structure in microelectronics. Again, different areas of structural engineering differ by different structures, different materials, and different loading conditions. So in this area, which is structural analysis of microelectronics and photonic systems, the typical structures is what you see here. It's a structure built of multi-material, different materials, different loading conditions, mostly thermal loading, but also dynamic loading. and also different approaches to evaluating the reliability, which are used in different areas. First of all, I want to emphasize that thermal stresses, speaking of thermal stresses occur at the ends of the assembly. It's not obvious, but it's certainly the case. Again, in my presentation, I'll try to focus mostly on situations which are not always obvious, sometimes even paradoxical, but when the analytical modeling can shed useful light on what happens. So interfacial thermal stresses occur at the ends of the assembly, and that has to do with the fact that in the mid portion of the structure, the structural segments are self-equilibrated by the forces acting within this component. By the end of the structure, the situation is quite different, and you need shearing stresses that outweigh the stresses acting in this segment, because these two resultant of these stresses and the resultant of shearing stress, they form a bending moment. We need also bending moment that would equilibrate this thermal moment, and this is the physical substance of the peeling stresses. But both shearing stresses and peeling stresses concentrate at the ends of the assembly. I've developed many years ago, you see, in 1986, I developed a theory which is widely used since then in not only actually microelectronics structural analysis, but in other structural analyses as well, is what I call interfacial compliance. And it's based on the fact that the longitudinal displacement in the layers of the bonded components which are adjacent to the interfacial plane, these displacements are higher and can be based on the hypothesis that is well substantiated and agrees well with finite element, is this displacement can be calculated as a loading independent compliance of the attachment and the calculated shearing stress. Another paradoxical situation is that these stresses do not increase with a further increase in assembly size, provided that the assembly is long enough. It's only in very short size assemblies. By saying short, I mean the actual width or length of the assembly, and also the factor which I call parameter of the interfacial shearing stress, that is a square root of the ratio of the on the longitudinal axon compliance to the interfacial compliance. And this is another important paradoxical but true thing that we should have in mind. We want to understand the physics and bring down the interfacial stresses. This is simple equations that can be applied to shearing stress. And for the peeling stress, I already indicated the nature of that. And these are simple formulas which were obtained by using a combination of structural analysis, well known in mechanical engineering, and theory of elasticity, also well known in applied physics and mechanical engineering.
Okay, I actually like the talk. May check out again. You all have the access to the pre-recorded video, and I hope this could be at least a precursor to get your interest and check out the full video recording. So with that, I think this is the last talk, and I would like to conclude our session, and I would like to thank all the speakers showing up today. And then yeah, so this is, and thanks for everyone for staying. to the end of the session. Okay, thank you. Bye-bye.
Thank you, Mr. Yang, for chairing this session. And now we are moving forward to our last session for today, which will start inshallah after the 30 minutes. So now we have 30-minute breaks.
Yeah.
So
okay. I have a talk in 20 minutes.
Oh.
No, not 20 minutes, 30 minutes. Yeah. Mm-hmm.
Okay, thank you.
Okay.
Thank you, Mr.
Okay.
Yang.
Bye-bye.
Bye. Hello, Mr. Akshay. Are you here?
Yeah, I'm here.
Okay, Mr. Akshay, you will be the chair for the next session. So after 30 minutes, we will start the next session.
Sounds good. Should I just stay in this session right now, or should I leave and come
No,
back?
you can take a break. You can come back
Okay.
after 25
Okay.
minutes.
Okay, thank you.
Okay, you're welcome.